important distribution is the Poisson distribution. So when does that occur? If we have an interval of real numbers partitioned into subintervals of small length delta t, and assume that delta t tends to 0. And the probability of more than one event in a subinterval tends to 0. The probability of one event in a subinterval tends to lambda delta t divided by big T. And they're independent of each other. We have a Poisson process. I have to say that that definition doesn't really help me too much to understand what it is. But say you have a number of raindrops falling on a car, for instance, at a moment when it's raining. That's a Poisson process. So you have discrete events which happen over a length of time. And so if you count that number of discrete events over a length of time, that is going to be Poisson distributed. And this is kind of important also in a lot of things we do as researchers, because a lot of the spectroscopy that we do has a Poisson distribution. And so if you have an analysis technique and you're shooting some type of radiation onto a sample, and you're measuring radiation coming off of the sample, that goes to a detector system. And so you're detecting the number of particles, for instance, which are coming into the detector, or the number of photons coming into the detector. So that's like the raindrops falling on a car. Okay, photons or electrons, protons falling onto a detector. And so it's important in that sense to understand a little bit about this distribution. All right, so we have events occurring at random in an interval. And so such a Poisson random variable, the probability mass function is defined by this equation. And the mean and variance, the mean is this lambda, and the variance is also lambda. Okay. So if, for instance, we have a spectrum, and we have some type of spectrum. Say we're looking at, typically you make a spectrum by looking at, for instance, energy windows, and the spectrum consists actually of a number of counts in each of these windows, right? You've had enough of materials analysis to know this? Or am I talking gibberish? It's okay, yeah. So say for instance here you have your peak value, which is 100 counts. Okay. This 100 counts, that's lambda. So this is your best guess of the mean value is the value you have. Lambda is the expected value of x, right? So that's the mean, and the variance is also equal to lambda. So that means that the standard deviation is equal to the square root of lambda. Okay. So if you have 100 counts, that means that your relative error would be square root of 100 divided by 100, right? So this is sigma divided by mu, right? So if you have 100 counts, your standard deviation on that value is 10 counts. right? So you have a relative error of 10%, right? So this is what is called counting statistics. So how do we get this error to go down? Say we want 1% counting statistics error. You increase the counts. So if you want 1%, we increase it to what? 1% error, what do we need to do?
100 times.
You have to multiply with 100, so you need 10,000 counts. Okay. So how do you do 10,000 counts? So you have 100 counts, I think 10% is not enough. So how do you now you want 10,000 counts. So you have a machine, you're measuring, the speed is really important to you. Of course with 100 counts, it's so I'm kind of fooling you here. With 100 counts, your thing may look like this, you know. Yeah, so you wait 100 times longer. So time times 100, okay? Your delta time. Okay, so say your experiment already took 1 week. To get 100 counts. So now you have to wait. 100 weeks is about 2 years. So that's a long time. Say you're doing your master thesis. This is now out of scope normally for the master thesis. Even master students don't have that much patience. So what can you do?
The scan velocity.
Say again?
The scan velocity.
The scan velocity.
Yeah.
Okay, say you have a technique where you're scanning, okay?
Yeah.
Now you go faster with scanning.
Yeah.
So what does that mean? You're scanning over, for instance, the energy axis here.
Yeah.
So your time per energy window is actually going down. So if you increase your scan velocity, you will have less counts per energy window. Okay. So if you want to do this, you have to scan 100 times slower, basically. That's what we're saying. So if you want to increase the time, you go slower. So there's some other issue, ways to deal with it. Yeah.
Set up 100 machines.
Yeah, use 100 machines. Good idea. Yeah. Or have a source, which is an alternative. So have the intensity of the source times 100. So you can go to a different machine which has a higher intensity, or you could use the same machine or increase the efficiency of detection. So if you had a small detector, you increase the area of the detector with maybe 100. So there's a bunch of things you can do. Alright. So of course the easiest thing is to wait longer, but sometimes you don't have the time. And so people may go to places where there's a very bright source. Instead of using, for instance, a copper X-ray tube, they may go into a synchrotron where there's a million times more intensity or something. Okay, so then things go much faster. And the basic reason why you do that is because of this Poisson statistics. Because if you just have a peak of 100 counts, as we said, you have an error of 10%. So you want to have more reliability, especially as the information becomes important. You want to be sure that it's there. The peak. That's what you do. All right. So when looking at your data, doing your master thesis or something else, where you have this Poisson distribution, think about this counting statistics error and see if that needs to be improved to be able to make a more substantiated statement. Okay. So some examples of Poisson distribution. So this is lambda point 1, 2, and 5. So you see what is happening. As we increase lambda, of course, the probability of having a higher value becomes larger. An example of using such a Poisson distribution. So, for me not to speak too much, and I just wanted you to go through the example. The process speed, which is
Elimination is a problem in virtual optical storage uses. So we have number of particles as a Poisson distribution. The average number. The area is 100 square centimeters. We have to determine the probability that 12 particles occur in the area of the distribution. Okay, first we need to note the number of particles in the area of the disk. So it's the area of the disk multiplied by the average number of particles. 10 particles. And then we just calculate the probability by the Poisson.
yes, I use the PMF for the Poisson distribution. Okay.
And it's like
So on the small x
Is this? Yes.
in this Poisson distribution
Mm.
is 12 in this case, right? So you have 12 here and 12 there, 12 factorial, and 10 to the 12. And this minus 10 that's the lambda, which we calculated here. Yeah, as 10 particles. Right. Okay, so that's how that works. All right, we can also then determine the probability there's 0 particles occurring. And that's this here. 12 or fewer, then you have to sum. It's like a cumulative distribution function that we're using again now. So I think you can do this once you know what these different values and parameters in such a PMF are. So if we have a binomial random variable, we can approximate it as a continuous distribution. And this is done in this way. So if we have, if we have this transformation here where z equals x minus np over the square root of np times 1 minus p, this z is then a standard normal random variable. So we can basically approximate a binomial random variable with this standard normal random variable this way. All right, so this is indicated here for p is 0.5 and 10 trials. Okay. So that works quite well if p is not too close to 0 and not too close to 1. So that allows us to then use a normal approximation to do calculations. So for instance, this is an example, transmission of bits, which we've done earlier. Now we want to see how well this works, this normal approximation. We have n equal to 50 bits, and the probability of an error is p is 0.1, and then the exact probability that 2 or fewer errors occur is then equal to this. You remember the binomial coefficients. We have 50n, this was x, and x has to be 2 or fewer, so we do this for 0, 1, and 2. And that gives us then 0.11. If we now do this based on a normal approximation, we do this transformation. And what do we have here? If we go back to this, so big X minus NP square root NP1 minus P. So this big X minus 5 square root of NP times 1 minus P, so N50 P.1, 1 minus P is 0.9, right? And so this has to be smaller than a certain value. And so we put here 2.5, why 2.5? Yeah.
It's a discrete random variable, so it doesn't matter if it's 2 or 2.5.
It doesn't matter if it's 2 or 2.5. Is that right? What do you think?
It matters because you go from a discontinuous variable to a continuous variable,
Yeah.
and the borders of your cell are go to a half to have the.
Right, so if you look at this thing here, for instance, so you put this kind of histogram representation, so you're looking at something which is smaller than as something which is between two discrete values. So that makes sense to take half between 2 and 3, to have things which are smaller than 2. And so this is then the probability of having the standard normal variable z smaller than minus 1.18, and if you look this up into the table, that's 0.12, which is fairly close to 0.11. Okay. So that works pretty well. And you can do the same for a Poisson distribution as well. So then you divide by square root of lambda, and you subtract also mean, so that you have the standard normal random variable. That kind of makes sense, because you want to subtract the mean and divide through the standard deviation. Okay. If we have more than one random variable and we want to do estimations of the probability of having a certain set of random variables, then the probability of having the random variables in a certain value range, if they're independent, is the product of the probabilities of having each of these random variables in that range of values. Okay, so that's something that is, of course, applies a lot of the times. So if you have independency of these random variables, there's something you can do. If you, for instance, problem here, we have a probability that diameter meets specification was determined to be 0.919. What is the probability that 10 diameters all meet specifications? Okay, so the specifications are given here. This is an example we've done the last lecture. So this is the range that we need to be in. And so if we expect independence, then we can just use the product, and so we then do the probability to the power 10 to find the probability of having 10 diameters all meet specifications. Okay. So you see that the probability of having at least one diameter not according to specifications is already bigger than 0.5. All right.